Hello, and I would like to perform a calculation for a real battery. That is to say, a battery that has real internal resistance and is not ideal, but let's assume ideal wires, and a single resistor which is known value, but the idea is that that single resistor could actually represent a resistor network. But for simplicity, let's just focus on a single resistor in this case. So let's read this problem. An old D-cell battery is measured to have a voltage of 1.55 volts when no current flows. When connected to a 2.30 ohm flashlight bulb, it supplies a voltage of 1.38 volts. Okay? So the idea is that real batteries have a certain voltage across them. So a D-cell battery is usually rated about 1.5 volts. But when current is flowing, it's delivering less than 1.5 volts because it has some internal resistance to this 2.30 ohm flashlight bulb. Okay, so we first want to know what is the battery's internal resistance and then what is the maximum current that that battery can provide. Well, let's have a look at our equations for a real battery. One of our equations for a real battery is the following: that the voltage difference available to the resistor load is going to be the EMF of the battery minus current times the battery's internal resistance. And then the other equation we should probably use is the fact that the current in the circuit is equal to the voltage difference that's available to the resistor load divided by the resistor load. Okay, now let's write down a few of our values. We measure the voltage of 1.55 volts when no current flows. So that should be the EMF. That's the voltage, maximum voltage possible from the battery when there's zero current. That's 1.55 volts. When we connect to a 2.30 ohm flashlight, so that's the load resistance, that's the large resistance when current flows, and then we supply a voltage of 1.38 volts. Delta V is 1.38 volts. Now notice, what this means is 1.38 volts, I believe, is 0.17 volts lower than 1.55 volts. And that means to say, because of the battery's internal resistance when current is flowing, that's right here, minus I times R here should give us 0.17 volts. But notice that I is unknown, but we also do not know the battery's internal resistance. Now this is really what we want to find. We really want to find the internal resistance of the battery. We're not asked to find the current in the circuit. So here's what I'm thinking. Given that delta V is what's available to the load resistor, and given that I we don't know and we're also not asked about, I believe that this I, this current in the circuit equation, should be substituted in for this I. And we should be able to solve for the resistance of the battery. So, delta V should equal to epsilon, capital epsilon, minus, and then the current becomes delta V over capital R, the load resistance, times the resistance of the battery. Well, we should be able to solve for this resistance of the battery. We can take this term and move it over with a plus, and we can take this term and move that over with a minus. So we get delta V times R times the resistance of the battery is equal to the EMF minus the delta V. Okay, So we can solve this for the resistance of the battery. Multiply by the load resistance, divide by delta V. So that should be resistance of the battery equal load resistance over delta V times EMF minus delta V. And that's algebra. Okay, so now let's put in the numbers. The load resistance should be 2.30 ohms. We also know the delta V is 1.38 volts. And then the EMF is 1.55 volts. And then the delta V is 1.38 volts. Okay, so let's calculate this value. The calculation becomes the following. It should be 2.30. We don't need to include the trailing zero because the calculator doesn't care about significant digits in the calculation. Divide by 1.38, and we have to multiply that ratio times the difference between 1.55 and 1.38. Okay, so let's hit enter. So I think we have 0.283. Let's write that down. R of the battery is approximately 0.283 ohms. Sounds good. All right. And then, how about the maximum current the battery can provide? So what if I just put an ideal piece of wire to both ends of the battery and allowed current to flow? The question is, what would be the maximum current? Well, the maximum current should be the full EMF divided by the battery's internal resistance, because that's the only resistor and the only voltage source in that case. So that should be 1.55 volts over 0.283 ohms. And we should be able to get that number as well. Okay, so let's get 1.55 divided by 0.283. Okay, so we've got 5.48 or so. Oops. So let's go approximately 5.48 amperes. Okay, so that ends this problem. Thank you very much for your attention, and I appreciate if you give this video a like and also subscribe to the channel to grow the channel, and I look forward to seeing you in the next video.